Good evening, everyone. I'm back again with the concept of signal conditioning, which we were seeing in the chapter number 3, that is the technological aspects of embedded systems. In the last some lectures, we have also seen the topics or the things like analog to digital converter or digital to analog converter. Similarly, some new concept or some new aspects of signal conditioning and what is the main role of this signal conditioning in the embedded system we are going to see today. So let us see in detail about this technological aspects of signal conditioning in embedded system. So before going in deep to this signal condition, let us know what do you mean by signal conditioning. So signal conditioning is nothing but a part of data acquisition system that interfaces to a sensor. Now as we have seen that the data embedded system is consisting of the things like sensors, actuators, input output interfaces, ports and the rest all things. So with respect to that, this signal conditioning is nothing but a part of a data which we need to interface with a sensor. Now this sensor is nothing but going to take as the input signals. So while taking this as the input signals, this signal conditioning is a part where the data acquisition system interfaces with the sensor. Is nothing but called as signal conditioning. So most of the sensors whichever we are required, some sensors require some type of accommodation to the turn their input into the linear voltage that can be measured by the data acquisition computer. Now whenever we are going to see that there are some sensors depending upon the application, the sensors quality the sensors we are going to change. So likewise, if we are going to use some kind of temperature sensors or soil moisture sensors or alcohol detector sensors, any kinds of sensor whatever you are going to take as an input, some kinds of sensors require the linear voltage to be measured at the input time. So this is done at the or this is measured by the data acquisition of the computer. So often the signal is too small and must be changed to the form that can be read by the computer or the sensor that needs the power. So this is nothing but called as signal conditioning. So now suppose when the signal, when this often most of the time whenever the input you are going to give to the sensors, it has been very small, is it not? So to change that the form to be read by, and that small signal has to be read by the computers, or it is needed or the sensor to be power. So this kind of signals whenever we are acquiring some data from the computer is nothing but called as signal conditioning. So signal conditioning includes, now what actually the signal conditioning means, the signal we are going to condition it. Condition means we are going to make it amplification, we are going to make the filtering of the signals, we are going to convert those signals, we are going to make excitations of the signals and the other techniques that are required to make the sensor output compatible with the data acquisition hardware. Now where we are going to see something about the hardware part, when the input is given to the sensors and that is compatible to the particular hardware. So with respect to that, whenever the input you are going to give to the sensors, first the thing required is you need to amplify those signals. Obviously whenever the input signal is low, we need to amplify it. So we need to filter those signals to remove some kinds of noises and all. Then we need to convert it, if it is analog to digital or digital to analog. Then we need to make it some excitations with some extra inputs to it, and then the other technical part whichever it is required to make that sensor compatible with the hardware output. So all these things are required for the data for the signal conditioning. So for the proper design of the signal conditioning module, it is critical for maximizing the accuracy for the DAQ systems. So we are going to see some common techniques whatever it is required to condition the input signals, like amplification is required, as I told you just now, amplification is required, linearization is required, filtering of the signal is required, isolation is required, simultaneous sampling is required, excitation is required, and the last is the cold junction compensation is required for the input signals. So let us see in detail about all these things or all these techniques one by one. So the first part we are going to see is the amplification. Now what is this amplification we are going to see? Everyone knows what you mean by amplification. So amplification is nothing but if the signal is smaller than the few volts. Now suppose we require 5 volt supply, is it not? We require 5 volt, and if that signal is less than the 5 volt, we need to amplify that to the accurate level of the 5 volt. That is nothing but called as amplification of the signals. And if it is large, and if the signal, suppose the required signal is 5 volt, and if we are having larger than the 5 volt signals, then if it is larger, then the maximum range of your analog input hardware, typically suppose it is 10 volt plus minus 10 volt, then what we have to do, we will have to divide that signal using our own register network. Yesterday we have seen by converting that analog to digital R to R ladder, or some kinds of techniques what we have used for analog to digital. Similarly here also we are going to convert those signals that into some register network and make it to the exact level what we are required. For example, if we need, there is a thermocouple generates a voltage that changes with the temperature, is it not? Whenever you are going to use the thermocouple, that is going to generate the voltage and that changes with the temperature. Now this called the thermoelectric effect, or the Seebeck effect you may call it as, which is caused by placing some metals into the contact to form the junction. However, the voltage is very small. Now, for example of a thermocouple, to generate the voltage, that is nothing but to come up with some particular temperature level, we are going to make up that generate the voltage that changes with the temperature. Now where the temperature is going to increase, the voltage is also going to increase. Simultaneously, vice versa, if it is going to decrease, the voltage is also going to decrease. Now this, whenever it is going to increase or decrease, this is called as a thermoelectric effect, or you may also call it as a Seebeck effect. And why this is caused? This is caused because we are going to place some metals in contact to form the junction. Now where the voltage is very small. Okay. Now where the most of the common thermocouples where we are going to use is the E-type junction, J-type junction, K-type, N-type and T-type. These are the basic 5 types of thermocouples which can change the voltage level up to 30 to 60 microvolt per degree. So if according to the per degree temperature, the voltage level has to increase or decrease. Is it not? The temperature has to change. So to change all these kinds of things, we are going to use the thermocouples, and those thermocouples can be used for the 5 different types: E, J, K, N and T, where these 5 types can change 30 to 60 microvolts per degree temperature. Now when it is done, the data acquisition device, then it has the 10 volt full scale range and 16-bit resolution. Therefore, only to detect the change of 3 to 5 degree or 5 degrees Celsius or larger, then this amplification is required. Now whenever you are going to acquire the data acquisition with a 10 volt full range supply and 16-bit resolution is given, that time what we need to do, only detect the change where 3 to 5 degrees Celsius is changed or not, or larger than that, and if it is changed, then therefore the amplification is required. So this is nothing but called as amplification, which is required for signal conditioning. Next we are going to see the linearity. Now the linearity must be corrected for almost any practical use of a thermocouple, is it not? So the linearity means what? According to the input, the output has to change, right? That is nothing but called as linearity. So by performing this, there are 2 methods to perform the corrections. First method is to look up the temperature every time by the voltages versus temperature you need to look. And the second thing is calculate the temperature using the equation. So there are 2 methods where you can check the practicality of the thermocouple, where the temperature is going to change as well as with the voltage, or you need to calculate, the second is every time you need to calculate the temperature using the equations, and highly both of them use the correct results. Okay. So the linearity correction is normally done in the software or PC, on a PC, where the complexity of equation is not a problem. So every time, first it is very easy to find. Whenever the temperature is increasing, obviously you need to check whether the voltage is increasing or not. That is nothing but called as linearity, and this method is done by using some kind of software on the PC. Okay, and for a device where not connected to the PCs, such as a standalone meters are been available. You might be seen in the physics where some kinds of meters are hanging meters are available, where you can stand it on a where you can make a standalone on the meters, where the temperature controllers are there, or many data loggers are available, and the linearity correction is done by the microprocessor in the device. So accordingly, the temperature sensor or temperature sensor and voltages changes are been given, it is applied directly to the microprocessor. This is nothing but called as linearity, where input changes, accordingly the output has to change. And next is by lookup table, may be the easiest. Now there is also some kind of lookup tables where we are going to have in these cases, accordingly the input, if the temperature is going to rise, change, look at the voltage, and you need to look up the table whether it is going to match or no. But a few extreme simple devices without a microprocessor do not have linearization. If you are going to use some kind of devices where there is no any microprocessor, then the linearity is not found in that device. This is about the linearity. Next we are going to see the filtering method. Now this filtering is nothing but the signal might contain the unwanted frequency components and the requiring filtering. Now as I told you, filtering means what? Any type of the signal, whenever it is going to give some input, some unwanted signals are going to get into it. So to remove that unwanted signal is going to have some extra frequency components in it. You all know, as the signal is going to increase, obviously the frequency is also going to increase. So that time, and that due to that unwanted signal, the output may not get correctly which is required. Might be the temperature is going to increase, the voltage is not increasing, or suddenly the voltage may increase due to this unwanted signals. So due to this, we are going to filter those unwanted signals, and due to this filtering removes the undesirable noise that could lead to error in the nervous environments. We know unwanted signals means what? It is nothing but the noise, and we have seen the noise. What do you mean by noise? Noise is nothing but the unwanted signals, and there are n number of noise which is going to get added with the signal immediately. Is it not? Whenever the input signal is applied, suppose some background noise has been produced at the background, then and that background noise is also going to get connected with the input signal, which leads to noise at the receiver side. So to remove all such kinds of errors, we are going to use the filtering methods. So slowly, while varying such signals or such temperature may require the low pass filters to remove the high frequency noise that can reduce the accuracy of your measurement. And rapidly varying signals such as vibrations often require as an anti-aliasing filter. We have seen all those things in the analog communication signals. What is anti-aliasing filter, or what do you mean by, or how to remove the signals noise at the receiver, and rest all things, which is nothing but given with the help of this low pass filter. You can remove the high frequency noises. Next we are going to see the electrical isolations. Now what do you mean by electrical isolation? Electrical isolation is nothing but whenever an electrical signal contains the high voltage component that could damage the computer. Is it not? So what you need to do, the sensor signal should be electrically isolated from the computer for the protection from the serious overvoltage. Now what we need to do, electrical isolation is the must technique where we need to look for the signal conditioning. So where we know whenever you are going to get the high voltage for your PCs, it may get damaged. Is it not? So for to avoid such kind of things, we need to keep the sensor signal should be electrically isolated all the time, so that from the computer to protect it from the over voltage serious damage. So the electrical isolations make sure that the measurement from the data acquisition system are not affected by differences in the ground potentials. For example, suppose the thermocouple is mounted on the windings of the motor. Is it not? So it may come in electrical contact when the high voltage wires are connected, is it not? So whenever the thermocouple is mounted on the high voltage wires, then what is the case? To protect this electronics from damage and to make the accurate measurement, we need to amplify that electrically isolated from the thermocouple. The amplifier is must required to by electrically isolation for that thermocouple, so that the required amount of voltage is only reached to the sensors. And some in the other cases, what we are going to see, when the hardware device and the sensor signals are reached to the reference to the ground level, then the problem occurs if there is a potential difference between the ground of each device. Now the grounding is also the most important part wherever it has been required, or else there is the earthing, what we called as, that is nothing but the earthing is also required. So that is the when the hardware device and the sensors signals are each referred to the ground, then the problem occur if there are the potential difference. If there is potential difference between these two, again the damage is going to occur with the signal conditioning purpose. So we need to look after the difference created noises and might lead to the enormous measurements. So for this purpose, to avoid that difference noise which is going to create some disturbances or which is going to create some errors, we need to see for the isolation, electrically isolation purpose. So using the electrically isolated signal eliminates the difference between ground potentials and ensures that the signals are accurately measured at the receiver end. This is all about electrical isolation. Next we are going to see is the simultaneous sampling method. Now this simultaneous sampling, we know what do you mean by sampling. Sampling is nothing but what analog signal is. Whenever you are going to give the input as an analog signal, that analog signal has been divided into discrete signals, is it not? That is nothing but done with the help of sampling. So there is a common technique for measuring this rapidly changing signals into the simultaneous samplings. So for rapid changing signals such as vibrations, due to vibrations, suppose there are vibrations occurring, then the input signal is going to fluctuate all the time, and it is important to measure the multiple channels at the same time, is it not? So they has to be compared. So simultaneous sampling does not have these separate amplifiers and sampling hold circuits. So in this system, without sampling and simultaneous sampling, the A to D converter samples and one channel as well as the switches to the next channels and the samples it and switches to the next channel and then continue this cycle. What we need to do at this multiple time, when we are going to get the multiple outputs at the same time, that time what you need to do is you need to get the output without simultaneous sampling. The A to D converter is going to sample one channel, okay. After sampling one channel, it is going to switch to the next channel, and again it is going to get sampled, and again it is going to switch to the next channel, and then again it is going to get sampled, and likewise the cycle is going to get continuously sampled outputs. So this effective sampling rate of each and individual channel is inversely proportional to the number of channels sampled, because A to D converter is having the sampling many channels at a time. This analog to digital converter. Now we know what do you mean by sampling. As I told you all, sampling is nothing but a method in which we need to convert analog signal into discrete form. Now discrete form means what? Actually we need to convert that analog signal into digital form. So A to D is the converter where it is going to sample each and every sampling output at a same time, and you are going to repeat those samplings each and every time. So care must be taken when using the multiplexers so that the switched signal has the sufficient time to settle. And so once the signal is settled, then the output is given to that particular respected channel and the output is not fluctuated, and which is going to give you the accurate result. Next we are going to see the excitation source. Now this excitation source means some sensors require some excitation source, that is nothing but the power is required to operate. Some sensor requires some external power to operate, or not external but even to the internal power to operate. For example, suppose strain gauges we are going to use. right? The strain gauges, if we are going to use, or we are going to use the thermistors, these requires the external voltage or current to operate. Now this signal conditioning modules can provide these signals. Resistive temperature measurements made by the thermistors need to have the current pass through it to the procedure measurable voltage output. So these examples, that is nothing but the strain gauges or the thermistor, where it is required external voltage to operate, the signal conditioning module provide these signals to it, so that the current has been passed through each and every possible measurement and gives the output accurately, that is the voltage output. This is nothing but called an excitation source. Excitation source means external power which is required for the sensors. And the last we are going to see is the cold junction compensation. Now this cold junction compensation is nothing but what it is, the thermocouple has a unique additional correction in it, that is nothing but called as cold junction compensation. And this is the unique among the temperature sensors, and it is often misunderstood that the reason for compensating in that thermocouple only reports to the relative temperature difference between the sensing end and the terminal where it is connected. Compensation is nothing but we need to look after the starting end and the receiving end, where the temperature is the difference or not, provided the difference between the sensing end and the terminal where it is connected. You need to look the temperature over there, you need to measure the temperature over the relative ends, and you need to check the absolute temperature of the connection must be known in order to calculate the true temperature and the thermocouple is measuring. So these are the two connections, that is the absolute temperature is known in order to calculate the true temperature, so that the thermocouple which it is measuring. So the absolute temperature for the connection is called as the cold junction, which is nothing but called as cold junction compensation. So the cold junction sensor is typically a semiconductor. What is this cold junction sensor? Is nothing but a semiconductor sensor or a thermistor, where it is located connection at the time of the terminals. So the temperature measured by the cold junction sensor is added to the temperature of the thermocouple. Okay, so whatever the temperature you have measured at the thermocouple, that is added with respect to that of the temperature sensed by the cold junction. So cold junction sensor temperature and the thermocouple is going to get mixed, and this is the simple procedure to follow for the subtle ramifications, that is nothing but to clarify the results, error results. So because of the cold junction compensation, the connection of the thermocouple is more complex than the other sensors. So the wire type and the location of the connection is more important in it. Which kind of wire you are using, what are the type of the wire you are using, and the location where it is been connected. It is the most important while measuring this cold junction temperature. Therefore, the voltage generated by the thermocouple results from the two dissimilar metals that has been placed in contacts, and which generates the voltage due to the thermocouple effect, that is nothing but also called as Seebeck effect, which we have seen earlier. And this voltage changes with temperature. And with each lid to the thermocouple must have the same type of the wires. Wherever you are going to lead the thermocouple terminals, while sensing those, it must have the same type of wire sensings where the cold junction sensor is located. So if you are going to take a copper wire which is connected to the non-copper wire thermocouple, then there another junction, thermocouple junction is created, and therefore the voltage across the new junction changes with the temperature. So we need to measure the same thermocouple changes or the same temperature at both the end. So if you are going to use one copper wire and one non-copper wire, then the temperature is going to change according to with the voltage. So same type of wire you need to take. Therefore the voltage measured would be the result of two junctions, and which is not expected. What we required is the cold junction temperature and the thermocouple temperature